we talked about binomial series, and here's a question. And it asks the following, that the Taylor series for f of x equals 1 plus 5x to the power q contains, and then there's a dot, 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 plus 7x cubed plus dot, dot, dot. Now, which of the following is a possible value of q? And there's 2 fifths, 3 fifths, 4 fifths, 6 fifths, and 7 fifths are given as possibilities. And I said binomial, and I said, just to help you remember, these are binomial Taylor series. So there's a way to compute binomial Taylor series. So what's going on? We're told the coefficient of x cubed. And now we're asked to figure out which power could it be. Now, the way this problem is phrased, it says, which of the following is a possible value of q? It turns out there are actually 3 values of q it could be, and I'll tell you what the other 2 are once we get our answer. All right. Do we have a guess? Sorry, what? D? E. It's not E, but it's a good guess. So, not E. Sorry, what? B is right. It is B, 3 fifths. All right, so the answer is 3 fifths. Okay, so what's going on? Well, we have 1 plus 5x to a power. Now, notice there's a box here. In our case, the box is 5x. So we say, okay, that's the sum of q, choose n, 5x to the n, which is really 5 to the n times q choose n. So you say, all right, let's look at the coefficient of x cubed. That would be if you plugged in n equals 3. So we have 7, because that's our 7, is 5 cubed, q choose 3. So I'm just plugging in n equals 3. And we work it out. That's 5 cubed times q minus 1 times q minus 2, 3 times 2 times 1. And we can distribute the 5s through. We say, well, you know, all the answers look like something over 5. So let's let q equal a over 5 just to make it a little bit easier. So we say, okay, we can multiply the 6 across. 7 times 6 makes 42. That's where the 42 comes from. Is a minus 5, a minus 10. So that's what we have. And now we just test. And you plug in 2. 2 doesn't work. Plug in 3. 3 works. You could actually stop. But plug in 4, 6, and 7, and none of them work. Of course, you'll see 7 was close. So E was not a bad guess in some sense. Now I said, I tell you what the other values are, and here they are. So if you said, I was thinking of 6 plus square root of 22 over 5, or 6 minus square root of 22 over 5, wow, you're ready. You're going to do great on that final. All right, any questions about this?
I have a question.
All right, we have a question.
Last lecture you introduced this choose operator, but
Right.
I never, before the last lecture, I never heard about it before. Because like I understand like multiplication, addition, but what this choose is, kind of why do we want this choose?
Well, why do we want to choose? In essence, you can say, for our purposes, it's just a convenient way of compressing this multiplication of all the terms out. But why the word choose?
Yeah.
Why does it come from? Well, if you're familiar with algebra, and you took algebra way back when, and you know, who can't remember our favorite 7th grade, 8th grade class when we said, oh, let's take 1 plus x squared and 1 plus x cubed. And maybe if our teacher was very bold on a day, 1 plus x to the 4th. And so we had this expansion, and we had these binomial coefficients. Now, so why choose? Well, it turns out that when you have whole numbers, and we don't oftentimes, this is for general. So there's no restriction on what alpha is. Alpha can be a whole number, it could be a fraction, it could be an irrational number. They all work.
Not function.
Not a function. But I mean, it could be, but to end up with the power series, we want to make sure we have just a number. And you might say, well, could it be complex? Yes, but that's a little bit too complex for us. So, but the point is, if it is a whole number, then it turns out that this binomial coefficient has an interpretation as counting something where you have a bunch of objects and you have to choose from among them a certain number. And so that's why we call it choose. When it's not a whole number, it seems strange to call it that, but that's the convention. So that's why we call it choose. Any other questions? So just to be specific, if I said 5 choose 3, that would say I have 5 objects and I want to pick 3 of them. So that's an example. All right. Well, this is our last topic, our last quote. And the last time always seems sad, but it isn't really. The end of one thing is only the beginning of another. Laura Ingalls Wilder, who wrote the Little House on the Prairie book, and others. And we've been together for a while, some of us. Some of us have been since the beginning of fall semester, hanging out, doing math, learning, and it's been a great time. But it's not the end. We continue. Some of us will continue to next semester and go on to Calculus 3 and other courses. But even if Calculus 2 is the end of the road, because that's all that's required, that's wonderful. I hope you've had a good time. And don't worry, you'll get to do math. Even if you take classes that don't have the name math in it, you'll still keep doing math. There's a lot ahead for you. This is not the end. All right. Well, our goal for today, not really any theory. Our goal is to say, hey, we spent a lot of time talking about Taylor series. We've been hyping them up. What can we do with them? We spent a lot of time, weeks and weeks, learning about sequences and then series and what does it mean to converge, what are power series, how do we make these Taylor series. Why did we spend all that time? So our goal is to talk about things we can do with Taylor series. We're going to talk about applications, and we won't necessarily get through all of them, certainly not today, but we can get through a fair number. So what do we have? Well, we have our function can be, in reasonable cases, at least certainly in the cases that we care about, written as a sum from 0 to infinity of the kth derivative evaluated at a over k factorial x minus a to the k. And in particular, there's already sort of 2 things to note. One is that, hey, we're storing derivatives, and in particular, our coefficients store derivatives. So that's why it says find a particular derivative. But also, it says, oh, we're approximating our function. And when I say approximating, we're really, really good approximation because we're equal. Approximating a function as a polynomial. And why do we want that? Well, because we're good at polynomials. We're really good at taking integrals of polynomials. We're really good at taking derivatives of polynomials. We're really good at multiplying polynomials and adding polynomials. We can do the math of polynomials. We can do the calculus of polynomials. So if we can transform our problem into a polynomial problem, it's a win. And there are problems that we can't do that we can now translate and say, hey, if we're willing to accept series, we can get the answer. All right. So I have a list here. We can find a particular derivative, find a Taylor polynomial, find some sums, determine indeterminates, which means we don't have to use L'Hopital. It's a L'Hopital alternative. We can find answers to integrals as series, and we can also do better estimates versus numerical integration. In some cases, not all the time. There are some things that we can't do, right? If you can't get the Taylor series, hopeless. Can't go anywhere. But if you can, it's oftentimes more efficient than trying to do numerical integration. So lots of things to do. Do you want to jump to any single one, or should I just go and... The first one. Start at the very beginning. It's a very good place to start. All right. So, this is an old quiz problem. We're given that the function is f of x sine of x cubed times e to the 3x. And we're told to find the 10th derivative at 0. All right. Now, do we need Taylor series to answer this question?
Yes.
Well, no. We can always take 10 derivatives, right? Will we mess up if we try to take 10 derivatives to answer this question? Probably. Yeah, probably we will. It gets messy. Really, really messy. And it's painful. We don't want to do that. We like ourselves too much. So you say, okay, let's not do that. All right, so we're not going to try to answer this question by taking 10 derivatives. So we're going to say, hey, we've got better tools. Let's use our technology. All right, so we know that our function, we can think of it as a Taylor series. It's the sum, 0 to infinity, the kth derivative at 0 over k factorial x to the k. So if I could find that series, then I win. Now the question is, do I need to find the whole series? Yes? No? No! What do I need? If I don't need to find the whole thing, what is it I do need? I just need to know what's happening with the coefficient of x to the 10th. And that's going to be helpful for us. Now, we do have a challenge in that we have our function is not one thing, it's two things multiplied together. But that's okay. We have the technology. We can either know or look up and we say, hey, you know, the sine of something, we have the formula. Sum 0 to infinity of minus 1 to the k, something to the 2k plus 1 over 2k plus 1 factorial. All right, so that's a nice true statement. I'm just going to mark the box here. And I know I keep putting boxes. I should put a Z or something. But I just want to just say, what's in the box? Make it abstract. So for us, what's in our box? X cubed. So we say, okay, sine of x cubed. Well, that's the sum. K equals 0 to infinity. Minus 1 to the k, x cubed to the 2k plus 1 over 2k plus 1 factorial. Well, let's start. What's the first term? K equals 0. Plug in k equals 0. What do we get? Negative 1 to the 0? 1. X cubed to the power of 2 times 0 plus 1, which, by the way, we could also have just written this part right here. This is the same as x to the 6k plus 3, right? 3 times 2k plus 1. So what power of x do we have? X to the 3. So we have x cubed. Divide by, downstairs, plug in 0, you get 1. Or 1. Very excited one. 1! Yes, but 1 factorial is also 1. Okay, now plug in 1. What do we get? Minus x to what power? 9. Divide by 3 factorial. Or 3! Yes, aha, 3! Someone's cracked the code. Okay, and then we don't care. Now you might say, Steve, that's harsh. I thought you were the person who cared. Well, why do I say we don't care about the rest? There's a reason we don't care. What coefficient are we after? X to the 10. What's going to be our power after this point? Yeah, the next one is going to be 15. But the point is, after this point, all the powers are bigger than 10. So they're off the menu. Because we only need to grab x to the 10th. Okay. Now, going to pause for a second here. There's going to be more work, so I'm going to put a line here. There's something that's going to go here. And then I'm going to say, hey, sine of x cubed e to the 3x. We just said the first part looks like, well, I'll write it as x cubed minus, and this is 1 over 6, x to 9 plus dot, dot, dot. Now we're going to multiply it by e to the 3x. Okay. So let's talk about the next part. We have e to the something. That's the sum 0 to infinity, something to the k over k factorial. That's just the formula for the exponential function Taylor series. All right. So, given that that's true, what's in the box? 3x. Okay. So e to the 3x, that's our sum, k equals 0 to infinity, 3x to the power k. I'll go ahead and write that as 3 to the k, x to the k over k factorial. Now, this one's a harder question. Given that we know we're about to multiply it by sine of x cubed, which powers of x do we care about and why? Now we could just write down a bunch of powers of x's. Definitely we could stop at x to the 10th. But do we need them all? Let's think about it. Imagine that we were running short on our pencil. Only a little bit of lead left. And like, oh, we don't have enough lead to write down all this stuff. Or maybe we just don't have enough patience to write down all these terms. What terms do we need? We are getting to the point where we are trying to say, hey, we don't care about anything other than what's in front of x to the 10. Now, we're going to multiply two series together. And so what we're going to do is we're going to pick a term from the first and a term from the second. Pick a term from the first, a term from the second. We're going to do it in all possible ways. But most ways are not going to end up in x to the 10. Anything past this point will definitely be above x to the 10. So, if I have an x cubed here, what do I have to multiply it by in here to get up to x to the 10? X to the 7. So, we say, hey, let's be smart. Let's talk about x to the 7. So, that would be 3 to the 7, x to the 7 over 7 factorial. That would give us an x to the 10. That's the only way to get x to the 10 if we use this x cubed. What about this x to the 9 term? Well, we'd have to multiply by x to the 1. So there's some stuff at the beginning, plus, plug in k equals 1, 3x over 1 factorial. And now we multiply. And of course, there's lots of terms that we're ignoring because we're hyper-focused. Say, look, we don't need a lot. We need something specific. We're after x to the 10th. And we say if we multiply the x cubed by the x to the 7th, or the x to the 9th by the x here, That's the only way we can multiply these two things together and get x to the 10th. So what's our answer to the coefficient? Well, we multiply 1 times 3 to the 7th over 7 factorial, so that's 3 to the 7th over 7 factorial, minus 1/6 times 3, so that's minus a half. Is this our answer? And why not? Okay, so first off, do you agree on the multiplication, perhaps? So if I want to get x to the 10th, I have to get it so that the sum of the exponents add up to 10. So x cubed and x to 7, multiply the corresponding coefficients. That's 1, 3 to the 7th over 7 factorial. Or x to 9, x to the 1. Multiply the corresponding coefficients. 1/6 times 3, that's 3/6, that's a half. And that's the only way we can pick something from the first and something from the second and get x to the 10th. So we're ignoring a lot. All this stuff here, the dot, 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 and all this stuff here, the dot, 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 there's a lot of stuff. We're just saying we're not worried about that because it's not getting us to our answer. So as far as the coefficient of x to the 10th, are you convinced about that? Is this our answer? And why not?
Do something like 10th derivative over 10th factorial equals something.
Right. This is, if we look at the formula, the 10th derivative at 0 over 10 factorial. We weren't after the 10th derivative divided by 10 factorial. We were after just the 10th derivative. So how do we get our final answer? We move the 10 factorial across. So we currently have, I'll write it again, the 10th derivative at 0 over 10 factorial. That's the generic coefficient of x to the 10th in a Taylor polynomial. And we said, hey, we figured out what the coefficient for x to the 10th is because we did the multiplication of the two series. There were two terms, 3 to the 7th over 7 factorial minus a half. So the last thing for us to do is we just need to move our 10 factorial to the other side. So our answer is the 10th derivative at 0 is 3 to the 7th over 7 factorial minus a half, all that times 10 factorial. And that is our answer. And that's a big number. So it's good that we didn't do it by taking 10 derivatives. We'd still be about the third or fourth derivative at this stage if we were trying to take derivatives. And starting to like, curses! Isn't there a better way? But there is a better way. All right. I see a hand up.
Why are you allowed to compare those coefficients when on the top where we have sum and we have f to the k over factorial, and it's like a sum, but there it's just like a polynomial. And why can't we kind of concatenate them, like compare? Is that why they are comparable?
Well, so we're saying that our original function, why are we allowed to do this? Our original function is we can write it as a Taylor series, which says it's a polynomial. And if you think about it, you say, change your mindset. Think about everything's looking polynomial. So we say, hey, sine of x cubed is a polynomial, e to the 3x is a polynomial. So I want to say something about polynomial which is equal to the product of two polynomials. So what's happening here is it's like, oh, we're really trying to multiply two polynomials together. But the thing is, I don't have to know the whole answer. I just have to know a little piece. So this is a practice in multiplication of polynomials. All right. Well, let's do a little cool down. That one's a challenging one. That was why it was a quiz problem back in the day. All right. Find P12x, the 12th order Taylor polynomial centered at x equals 0 for the function f of x equals x squared over 1 plus 2x cubed. All right. Now, this seems counterintuitive. We're asking for a Taylor polynomial, but I'm saying let's approach this as a Taylor series. And at that point you're saying, but wait, hold on. Taylor series seems to ask for a lot more. Because if I'm looking for a Taylor series, it's like I want to know all the derivatives. But if I just want a Taylor polynomial, it's just like I need to know all the derivatives up to some point. So it seems counterintuitive to say I can use a Taylor series to help me find a Taylor polynomial. However, we can make progress. And that's the cool thing. All right. So if we were to just put on our Taylor polynomial hat, what would be the steps in finding P12 of x? So let's ignore that we could have a Taylor series approach. If we were asked to find P12 of x for a function, what would you need to do? Take up through the 12th derivative. So you'd have to take all the derivatives up through the 12th derivative. What would you have to do with those derivatives?
Set up, plug in our formula.
Well, you have to plug in at the point you're centered at. And those help you find your coefficients, and you put it all together, and you get your answer. But now, we made an observation. And I'll just make a note of it here again, which is if we find a series, then it is the series. So if we can find a way to represent this as a series, then we have found the series. Okay, so now we look at our expression and say, does this remind us of any particular one of our series? We only have 4 candidates. Well, we have 5 now with binomial. So as a reminder of what they are, we can do e to something. This doesn't look like e. Sine of something, cosine something. This doesn't look like either of those. We can do binomial, and we can do geometric. Does this look like any of those? Geometric. Let's remind ourselves of geometric. So geometric says 1 over 1 minus something is the sum of something to the kth power. So that's just the generic way to write geometric as a series. Now, the x squared on the top, we're perfectly fine with that. We are comfortable with the x squared. The reason we're comfortable with the x squared is it's a polynomial. We like polynomials. So we can just start by saying, well, what do we really have? We really have x squared over 1 plus 2x cubed. And that's x squared times 1 over 1 plus 2x cubed. So the x squared, this part we're happy with. This part we're warming up to. Now, are we ready to say what's in the box? And if not, what do we need to do? Yeah, we need a minus. This is a plus. How do you turn a plus into a minus? Minus a negative. So this is 1 over 1 minus 2x cubed. Okay, so now we're in the right form. We have 1 over 1 minus something. So we're able to say, hey, we have our box. It's this minus 2x cubed. That's what's in our box. So we say, okay, we'll write down our series then. So we have that this is x squared times the sum, 0 to infinity, minus 2x cubed to the k power. And at this point we can do two things. One thing we can do is we can bring the x squared inside, because that can distribute in. And the other thing is that we can break up this minus 2x cubed to the kth power into two parts. So this becomes the sum. We'll have minus 2 to the k power, x to what power? 3k plus 2. All right, because we have 3k plus 2. All right. So that's the series. How do you go from the series to the polynomial? So if the series says, well, we never stop, never stop, never stopping, what does the polynomial say?
Never stopping.
Well, the series says never stopping. Polynomial says
Never stopping. I don't know.
well, series says never stopping. So what's the opposite of never stopping? Stop! You go and you stop. Okay, so the Taylor polynomial is basically just the beginning of the Taylor series. The question is, how much do you take? So how much of this series do we have to take? Where's the clue? As I point to a number. 12. Now, we just need to go up until we hit at most 12. Now, we may not hit 12. It's possible, because the order of the Taylor polynomial doesn't necessarily say that's our biggest power. But we're going to stop and say anything past order 12 we drop. So we start writing down the terms. So we plug in 0. Negative 2 to the 0 is 1. Then you have x to the 0 plus 2, x squared. Okay, plug in 1. Negative 2 to the 1, negative 2. X to the k equals 1. 3k plus 2 is 5. Plug in k equals 2. Negative 2 squared, 4. So plus 4. X to the k equals 2, 8. Plug in 3. Negative 2 cubed, negative 8. X to the 3 times 3 plus 2, 11. Now what's going to be the next power? 14, which is above 12. So we say, okay, and plus dot, dot, dot. And now we say, hey, good news. This part right here, and just to emphasize what happens here, I'll go ahead and write the next term. The next term would be plus 16 x to the 14. You only need to go up to where you have at most power 12. So this beginning of your Taylor series, they're all Taylor polynomials. It's just how much do you want it to approximate? We wanted it to approximate up through the 12th derivative. So this part is our P12. So the beginning of a Taylor series is the Taylor polynomial. So if you have a way to make your Taylor series without having to go through and take derivatives, that can give you an alternative to finding your Taylor polynomial. This is similar to an exam problem from a few years ago off the final exam. So this isn't just a random problem.
So like this 12.
Uh-huh.
Like before, I thought that it means like 12 terms, but it is not, right? Like it's not that we need like 12 terms. It just
right. So
it tells power.
So 12 here refers to 12th order. And so the 12 refers to how many derivatives are you trying to match. Now in terms of the series, every coefficient is storing a derivative. So the coefficient of x squared is storing a derivative, and it says, hey, your derivative is 2. Now you might say, wait, the coefficient's 1. But you have to remember there's a 2 factorial involved. So every coefficient is storing a derivative. What's our coefficient of x cubed? 0, which tells us our derivative of the third derivative is 0. So when we talk about the 12th order, we're saying we want to match up to the 12th derivative. The powers are telling us which derivatives we're giving information on, and we're not writing terms down. So there's really a 0 plus 0x plus x squared plus 0x cubed plus 0x to the fourth minus 2x to the fifth, so forth and so on. So we just have to get up through x to the 12. Now, I'm suppressing these 0 times things, but the point here is this tells you how many derivatives we're matching, and the derivatives are the coefficients. So we just have to get up through all the terms which have power at most 12.
So minus 2, 4 is the derivative?
So minus 2 is the coefficient of x to the fifth. But what is the coefficient for x to the fifth? It's the fifth derivative divided by 5 factorial. So minus 2 is the fifth derivative divided by 5 factorial. So it's not that minus 2 is the derivative, because there's that factorial involved.
Where is this sort of right now?
It's just not, we just didn't write it down. We could have, but we don't write it down by default. So, I mean, underneath here we have the same f0 plus f prime 0 x plus f double prime 0 over 2 factorial x squared plus f triple prime 0 over 3 factorial x cubed plus the fourth derivative at 0 over 4 factorial x to the fourth plus the fifth derivative at 0 over 5 factorial x to the fifth, and so forth. I'm running out of space. But the punchline here is you say, hey, this minus 2 is this. The fifth derivative at 0 over 5 factorial. So just for convenience, we don't write it down because it makes it harder to compute. The point here is that we know that if somebody says, okay, now tell me the fifth derivative, it's like, okay, there's going to be a 5 factorial that needs to show up that we have to keep track of. All right. How are we doing on time? Okay. We might go into Friday at this rate. All right. I think we can get one more done, but it has to be the right one. Maybe we'll do this one. This one's a fun one. A nice cool down problem.
You don't laugh at this.
So write 2 over 4 plus 3x as a Taylor series, centered at x equals 0, and as a Taylor series centered at x equals negative 2. Now, I won't beat around the bush. Of all the things that we have Taylor series for, when you see write something as a Taylor series, your reaction is, we are not taking derivatives. That's off the menu. The only way we're going to write things as a Taylor series is we're going to take something that we have and modify it. And of all the things that we have, this looks most like geometric. So we're going to have our geometric series at our disposal. So we'll just make sure we remind ourselves of that. Okay, so we want to write this as a Taylor series centered at x equals 0. What do we do? Okay, someone has suggested we take out a 4. All right, so we have 2 over 4 plus 3x. I'm assuming that we'll take the 4 out of the denominator. So that would give us a 1 plus 3/4 x. Should we do anything with the upstairs? Take out a 2? Why not? All right. It does feel more geometric-y, yes. But what else do we need? Yeah, we have to fix the minus, which we talked about before. So this is 1/2, 1 over 1 minus 3/4 x. And now we're like, oh, perfect. So this becomes 1/2 sum. We know what's in the box, minus 3/4 x. So we have sum k equals 0 to infinity, minus 3/4 x to the k. And if we want to, we could bring this 1/2 in, and then we could distribute this k power through. So we could say this is the sum from 0 to infinity of 1/2 times minus 3/4 to the k power x to the k power. Okay, so that one wasn't too bad, which is good because we didn't have much time. But then there's the second part. It says, hey, same function. We're not changing the function. But now we're not going to be centered at 0. We're going to be centered at -2. Okay, so before we jump in, let's just think about it for a moment, but not too many moments because we're almost out of time. If we're centered at -2, that says, hey, we need to look like sum k equals 0 to infinity, f to the k at -2 over k factorial times what? X minus -2, which is x plus 2 to the k. All right, so this part right here, this is just a number. That's not the point I want to focus on. I want to focus on, oh, I see here an x plus 2. So if I want to write it centered at -2, I want to make sure I see x plus 2. So how can we make something into an x plus 2? We have our 2 over 4 plus 3x. When I see x, I want to see it as x plus 2. So what do we do? If we want it to look like x plus 2, we put x plus 2, right? It's an easy solution. But we can't just do that, because that feels like cheating. So how do we fix it? So I can subtract 2 right away, but notice I have this 3. So if I do it like this, what do I need to subtract? -6. Yes, because 3 times 2 becomes 6. 6 minus 6 is 0. So now I haven't changed it. I just said, hey, wherever I see x, I'm going to make it x plus 2. Or if you like, this is 2 over -2 plus 3 times x plus 2. Now, what can we do? From which one? The top or the bottom? Haha, trick question. Do it both. So we'll pull 2 out of the top. Actually, what will we pull out of the bottom? Yeah, -2. So, sorry, I gave myself too big a fraction. 2 over -2 times 1 over 1 minus 3/2 x plus 2. Now the 2 over -2 becomes -1. And what can we do here? This is 1 over 1 minus something. We have our box. So this becomes our sum, 0 to infinity, 3/2 x plus 2 to the k. So we can write this as, we'll just leave the minus in front, sum, k equals 0 to infinity, 3/2 to the k power, x plus 2 to the k power. And there we go. All right, that's the end for today's practice, but we're only halfway through, so we'll keep going on Wednesday.